Happy Thursday, everybody! We're going to continue in our lesson on the instantaneous rate of change, where the only thing constant in life is change, and learning how we use mathematics to measure different types of change. So what we've been learning about is instantaneous rate of change, and it begins with the concept of the secant line and moving a secant line closer to a specified point and closing those intervals. And we learned that as we close our intervals closer to one point, we arrive at what we call the tangent line. And the slope of the tangent line is the instantaneous rate of change at a particular point. Then we asked ourselves the question yesterday, is there an easier way than constructing intervals to find the slope of a tangent line, not just at one point, but at many points throughout a particular function? And we said yes, by finding the derivative. And the definition of a derivative is a new function that gives you the instantaneous rate of change at each point of the old function. And so the derivative was found yesterday by using certain derivative rules that have already been derived for us in what we call differential calculus. So that was the first thing that we did, was find the derivative of a function. Now, the next thing we're going to do today is the second part where it says, and the slope of the tangent line for each point on the curve, is we're going to start finding the slopes of the tangent lines. So, as we begin, here's a picture of Sir Isaac Newton, who was the one who first got started with instantaneous rate of change and instantaneous velocity. And we need to remember that we are measuring the behavior of a function at a certain point. We're not creating or solving for a new point or value. We're simply taking a measurement of how the function is behaving. So the function can be increasing, decreasing, or staying constant. So here's the 4 steps that we're going to follow today. We're going to find the derivative of the function, solve for the slope of the tangent line, write the equation for the tangent line, and graph the function and the tangent line. All right, so here's our 2 examples that we have today. So our first example says, given the function f of x equals negative x squared plus 4x plus 1, we want to find the instantaneous rate of change at the following 2 points, x equals 1 and x equals 3. So let's go ahead and do that. Let's start with, first of all, writing the function, which is going to be f of x equals a negative x squared plus 4x plus 1. So the first thing that we said we're going to do is find the derivative of the function. So I'm going to write f prime of x, and the derivative is going to be a negative 2x plus 4. And that's using the derivative rules that we learned yesterday. So if you need to, please have your note sheet out from yesterday that the Google Doc that shows you the derivative rules. So now that I have found my derivative of the function, and I want to find the slope or the rate of change at x equals 1, I'm simply going to do f prime of 1, because the second step we said was to solve for the slope. So what I just found here, this is the slope of the tangent line. So what I need to do now with my slope of the tangent line is I'm going to use the point slope form of a linear function to write the equation of the tangent line, and that way I can graph the equation with the equation of the tangent line. That way I can graph my tangent line. So let's look at what I know here. I already know that my slope is 2. X equals 1 is my x1 value. So what I need to discover is what is my value for y1. So one way that I can do that is if I go to Desmos, and if I graph my function on Desmos, if I come over here and graph f of x equals negative x squared plus 4x plus 1. All right, so I get a graph that looks something like this. So what I'm looking for is what is my y value where x equals 1. So if I come over here to my graph, here's where x equals 1. Here's 1 on my graph, halfway between 0 and 2. So if I read up to where I intersect the graph and over, my y value is going to be 4. Everyone see that? I read up and over. So now I'll come back here, and my y value, or my y1, is going to be 4. So now I simply finish my point-slope formula. So when I distribute the 2 to everything in parentheses, I get y minus 4 equals 2x minus 2. Then I add 4 to both sides. And my answer is y equals 2x plus 2. So now I have found the equation of the tangent line, and I can come back over here to Desmos and graph the equation of my tangent line. So if I look here where x equals 1, there is the equation of my tangent line. As my tangent line is by using the equation of my tangent line. So that's for x equals 1. Now the problem also wanted us to find the instantaneous rate of change for x equals 3. So what I do then is come back over here, and I'm going to use my same derivative. So my derivative was f prime of x equals a negative 2x plus 4. So I'm going to use my same derivative. This time for x equals 3. So now I'm going to put 3 All right, so what I just found here is the slope of my tangent line is negative 2. Okay, so I come over here where I can now do my next step, which is to write the equation of the tangent line. So I know here that my slope is negative 2. And then 3 is going to be my x1 value. So I need to find y1. So again, I'm going to come back here to my graph on Desmos and look for x equals 3. So here's 2 and here's 4. Halfway in between 2 and 4 is 3. So again, I read up and over, and I see that 3 is also going to be 4. As I read up to 3, it intersects the parabola at 4 on my y values. So I come back here and I put 4 in for y1. Now I simply distribute. So there's the equation for my tangent line at x equals 3 is y equals a negative 2x plus 10. And so what you just did is you just used the derivative of a function to find the instantaneous rate of change at multiple points along this particular parabola. So that's the purpose of the derivative, is the derivative allows you to find that instantaneous rate of change, the slope of the tangent line, and to write the equation of the tangent line without developing all those intervals like we were having to do on our previous exercises. All right, so let's go ahead and do example number 2 together, which says f of x equals x squared plus 3x. And again, we need to find the instantaneous rate of change at the following points: x equals -3 and x equals 1. So we'll begin again with, here's my function, which is going to be f of x equals x squared plus 3x. And the first point I'm going to look at is x equals -3. So first thing I want to do, according to the 4 steps, is I want to find the derivative of the function. So using the derivative rules from yesterday, this becomes 2x plus 3. That's the derivative function. Now I'm going to solve for the slope. So I simply input the -3 into the function. All right, so what I again found here is the slope, or the rate of change, for this particular point, -3, is -3. So again, I write y minus y1 equals m times x minus x1. And okay, so I need to find my y1 value. So again, let's go ahead and go over to Desmos. And this time, we're going to graph our function, which is y equals x squared plus 3x. All right, so here's my function. And for x equals -3. So if I look right here, here's -3, where x is -3. My y value is 0. Okay, so that means y1 is going to be 0. So let's go ahead and distribute. So here, 2 negatives make a positive, so that is really going to be -3 times a +3, which is going to give me -9. And this 0, y minus 0, is going to be y, so we're left with just y equals -3x minus 9 as the equation of our tangent line. All right, so what that tells me is my instantaneous rate of change at whatever this function is modeling is a slope of a -3. And in this case, it just happened to be the same as my x value. Okay, so my next one was to find for -3 and for x equals 1. So again, let's start with the derivative that we found in our previous example, which is going to be f prime of x equals 2x plus 3. And this time we're looking for x equals 1. So for this example, the slope of my tangent line is going to be 5. All right, so I know my x1 is going to be 1. So let's go find my y1. So I'm looking for the point where x equals 1. So here's 0, here's 2, so 1 is in between. So I start at 1 and I read up, and my y coordinate there is going to be 4. All right, we read up and over. So I'm going to have y minus 4. And now I just go ahead and distribute. So there is the equation of my tangent line. Now that I have the equation of my tangent line, I can graph that line. So there's the equation of that tangent line, and let me type in the other one so we can see them both together. That's what I'm. All right, so there we go. So there are both of my tangent lines. So as you can see, the derivative of the function allows me to find the slope of both of those tangent lines and to graph them without having to make all of those intervals like we were doing before. So what you have for today, and actually I'm going to make this due tomorrow since this is a little bit more work than we normally do. So there's 5 problems for you to do where you're going to be finding the derivative of the function, doing the 4 steps that we've just been doing, solving for the slope of the tangent line for both points, writing the equation of the tangent line, and then graphing the function and the tangent lines. Okay, if you need any help with this, please contact me on Google Meet, or you can send me a message through Google Classroom. Have a great day, everybody. And remember, this is due Friday, so you can do part of it today and part of it tomorrow, or however you would like to do it. This is going to be due, all 5 problems due Friday. All right, have a great day. Have a great Memorial Day weekend coming up. And I will have something for you on next Tuesday. Goodbye.